So I'll just introduce our keynote speaker for the morning, who's Jafar Hussain, who's going to talk to us today about some work done at Netflix.
Short and sweet, all right. Hi, everybody. Welcome to my talk. It's called Falcor. I'm from Netflix. Really, I think the theme behind this presentation is that I think most users really want to believe the entire cloud is sitting right there on their device. And so Falcor is a project that we came up with at Netflix. And what our conception was really that we wanted to be able to code that way as developers. We wanted to be able to basically imagine that all the data on the cloud was sitting right there on the device. Now, there are lots of frameworks to try and do this. But really, over the last 3 years, we've kind of radically reimagined the way that clients talk to the server. And we think it's, it's definitely unique, if not innovative, certainly a combination of things that hasn't necessarily been done in this particular way before. And so I'm interested to talk to you guys about it. A little bit about myself. I'm Netflix's cross-team technical lead. I am the architect of Falcor, and I'm an active participant in the TC39. Who's heard of the TC39? I'm just curious. That guy. Okay. It is the JavaScript Standards Committee. And so we're helping to shepherd the JavaScript language and evolve it. Don't throw anything at me. We're trying our best to make it better. So let's just rewind 3 years. 3 years ago, Netflix had what I'm going to say with some reservations is a RESTful API. This was a very conscious effort on our part to try and create a RESTful API. Essentially, what we wanted was we wanted resources and we wanted HTTP verbs. We did not do hate AOS, which is hypertext is the engine of state, but we basically got pretty close to a RESTful API, and the idea there was to try and mimic the fact, try and really account for the fact that Netflix is a browsing problem. Although Netflix gets a lot of new content all the time, within the context of an individual user session, it's mostly a large catalog that's static that you're browsing through. And so looking at REST, of course, which is an architectural style derived from the World Wide Web, which is by far the most successful browsing system ever created, we thought, well, this probably has some application to Netflix. That wasn't the only reason. Of course, it allows us to be loosely coupled, and the idea would be that other people might be able to build things with Netflix and use our APIs to build more interesting systems. So there was really two goals there. But I think primarily what we were interested in was some of the benefits around REST around cache coherence, caching. When you're dealing with large volumes of static information, as much information as you can catch, and the simpler your caching architecture, the better, really. And so we started out with this wonderful view of how RESTful our API was going to be. And over time, we went from having a RESTful API, not by design, but just sort of through I think, lack of care, to what I will call a REST-ish API. Sort of REST-ish, REST-adjacent, maybe you might call it. We started to cheat. Developers, one at a time, started to demand more and more of the API, and basically it became less and less RESTful and more like RPC. And so we began not grabbing entire resources. We began dividing resources up and repeating information among multiple URLs, not essentially getting the cache coherence benefits we were looking for. And finally, it degraded into pretty much just RPC. We stopped doing REST, we started doing RPC and using these URLs purely as procedure calls, and we relied heavily on query string parameters, basically passing parameters to procedures. So why did this happen? I mean, why would Netflix move away from REST? And as I said, it wasn't by plan, it was very organic. Because as I mentioned, Netflix is a browsing problem, primarily. Something interesting has happened over the last 10 years, and that is that the web was once a place to get things, and of course it's still a place to get things, but now also it's increasingly a place to do things. And so we've moved away from browsing large amounts of static content on the web, and we're now building web applications. And web applications, as opposed to web pages, tend to deal with large volumes of small resources. And so web servers tend to have very large resource boundaries, HTML, images, for example. But when you get into web applications, you're sending structured data, and you're often sending a very large number of small pieces of structured data, each of which can be considered a resource. So an individual piece of video metadata in Netflix might be very, very small, might be only a few properties. And it's easy to see how HTTP headers, for example, in some cases could even dwarf the message itself. And so sticking to RESTful principles, well-intentioned though they may be, can end up hurting performance in terms of latency, particularly when you're talking about mobile devices. So here's an example of a fine-grained resource that Netflix deals with. It doesn't get there are a few properties redacted here to help it fit on a PowerPoint slide, but it's really not much bigger than this. Now, you can imagine the implications of making, say, 15 or 20 of these calls just to render your starting page in Netflix. Right? So we tried this. We didn't spend very long trying it because it was clearly not a good idea. So by the time I'm finished talking, hopefully this will have loaded. That's about how it worked in real life. So we made a lot of calls, and of course, at the time, we're talking HTTP 1.1. And so these calls were actually sequentialized. And even if there was pipelining or multiple connections open, browsers at the time didn't necessarily support a lot of concurrent connections. And so really, despite our best intentions, we just had to move away from REST for performance reasons. And that's not surprising, given that Roy Fielding has himself said that REST is an architecture designed for large-grain resources. And so as you move into web applications, there's a lot of talk, really, about leveraging RESTful APIs. And I think a lot of it may not be a lot of developers may not understand really the implications based on the types of web applications that we're trying to build now and how responsive they are and what it really means to build a RESTful API. I suspect that we are not the only ones cheating out there. I suspect there are a lot of people who start out with these intentions and then begin cheating and end up with something not quite RESTful. But of course, why do we want REST? Well, we want cache coherence. I mean, cache coherence is a wonderful property, right? The idea that if I keep all of my data about a particular entity in one URL and then do not spread that data out, well, it's wonderful because, of course, I can rely on the browser cache. And then we can leverage all of that wonderful infrastructure that's out there on the web for caching information, right? Not just on the client itself, but across multiple tiers in the network. And so having, say, personalized recommendations and titles all as separate URLs really, really helps you. At first, the data load is very, very long. But after that, it performs very well. Unfortunately, user perception, and this is not something that jives very well with the way users perceive software, they tend to have their attention highest when software loads. And so although it might be the right architecture for them long term and might produce the best overall performance, when attention is highest with the user at the beginning, it tends to produce terrible performance. And so what we want from REST is we want cache consistency, and we want loose coupling. But we didn't want the high latency, and we didn't want the large message sizes. And so back to RPC. Now, from my perspective, what RPC is, and I think there's probably a lot of people in here who have applications like this, really what it comes down to is one or more endpoints specifically designed for your views. And so at Netflix, we would have an endpoint for the gallery page, we have an endpoint for the movie details page, we have an endpoint for search, and we'd have, a series of these endpoints. And they're all really effectively tightly coupled to the view. And if I wanted to, say, add another field to a particular view, I might have to go to the server guys in the back end and ask them to then add that field to the message. And that became problematic. It's not just problematic when you're going across organization, right? The tightly coupled APIs, it definitely makes it harder for other people to build interesting apps on top of the Netflix API. But even within an organization like Netflix, where you have multiple UI teams with diverging views, the server teams started to get really, really bogged down, trying to add all sorts of little extra query string parameters and extra options and additional endpoints for every single UI team's specific use cases. And so one solution to that is to allow client developers to write server code. And that was the first thing that came to mind. They were like, well, why don't you guys just do it? We want to get the hell out of this, out of your way, and you guys can write the endpoints. But I think that probably would have doubled down on an architecture that has a lot of downsides, right? We would have ended up with a lot of RPC calls. And of course, there's some downsides to that, and I'll talk about those in just a moment. So, of course, the upside, though, is run requests per view. I mean, when we're talking mobile devices and you're over a 3G connection, not having 3 or 4 sequential connections makes a tremendous difference. And so it's often worth it to sit down and write a specialized endpoint for each particular view. That said, that comes with a certain amount of complexity cost. So in this case, instead of taking the entire video resource, we can narrow it down, at least for gallery view, to the 2 fields we absolutely need, which is the URL of the box shot and the ID of the video. And then we can have one big message which contains all of the titles. And so just one request. We've loaded everything you need with the smallest amount of data hit to your mobile device. But of course, we end up sort of gerrymandering resources. For those of you who don't know that term, it's when Congress redistricts and sort of draws district lines just to, the folks who might be more likely to vote for them. And it's why the American electoral map looks kind of ridiculous. And that's effectively what we're doing here with resources. There are HTTP resources. A video is a resource. It's legitimately a resource in Netflix. But what we're doing is we're slicing and dicing it And we really, at this point, we can't really cache this at the HTTP cache level, because we may have multiple URLs which contain that same fragment of video title. And then at that point, we may end up with stale data, because even if we invalidate one particular URL with a put or a post, for example, then we might hit another URL and end up showing stale data. So if I choose to rate a video, right, it's a problem if 3 or 4 different URLs happen to have that same rating in their message, because if I go to another one, I may have rated a video and then go and see stale data. So, we don't want to be in the business of cache management, and that's basically what RPC did to us. Now, on the surface, RPC actually should be decoupling, right? One of the wonderful things about procedures is that they're black boxes. I don't have to know what the black box does, I just call it. And so in practice, we should be decoupling. And it might seem odd to say that we were being tightly coupled to these procedures, but there's an exception to that rule. You are tightly coupled to a procedure call if you have a cache. The problem with a black box is that if you happen to cache the entities behind that black box, it's not really a black box anymore, because as soon as you call that function, you need to know exactly what it does to the data out there on the server so you can keep your cache up to date. And so you really get the worst of all worlds. You sort of get very tightly coupled, and you also have the cache management problem. Now, since we can't use the HTTP cache, and yet we want to use caching, the only option for us for a single-page web application is to do in-memory caching and basically manage the cache ourselves. And so that means we need to know the types of messages, the fragments of the title coming from these different procedures, and sort of mix them in to an ad hoc in-memory cache. And we don't want to be in the business of doing that because it's a tremendously complex problem, right? It's one of my favorite quotes here from a former Netscape developer, only 2 hard problems in computer science. And I definitely want to avoid the latter. First one can't be avoided. So what we want from RPC is we want low latency, we want small messages, but we don't want the tight coupling, and we certainly don't want to do manual cache management. And so we took a look at the positives from both these architectures, and we wanted to know if there was a way to combine them, or at least to try and combine them as elegantly as possible and take as few of these trade-offs. And so Netflix did a lot of deep thinking about that. Really, what was on the table, as I said earlier, was having every developer be able to write their own endpoint. We were concerned that over time that would lead to more fragmentation and very little code reuse across teams, where at the time, certainly 3 years ago, there was very little code reuse and quite a bit of fragmentation already. And so after a bit of thinking about the problem space, we came up with what we call FalCore. And really, if I was to sum up FalCore in 3 words, it would be one model everywhere. So what we did was we started to try to work with the concepts that developers were already familiar with, things like JSON, for example, things that they were comfortable with, and then try and model the cloud as JSON, basically a model in memory. So with FalCore, what you can do is you can start working with a JSON API on the client, and then later on, because you're working with it through a proxy, you can take that data and you can remote it to the cloud. And so the API, however, on the client doesn't change. It's basically the same as JSON. You look up a series of keys. Now, in practice, you don't necessarily have to have that JSON model out there on the cloud stored on disk or stored on memory. In fact, it can be what we call a virtual model and can be assembled on the fly when requested from various different data sources. And so that's really the goal here, is to try and take the complexity of the Netflix backend, which can involve actually over 80 services, and make it look like a simple JSON object in memory that developers can even bind to directly in their view templates. So the way you work with this is it's just the data. There's no special API to this. It works like a JSON object. You look up series of keys, and so I'll show you an example. Here's how you would look up the address of a person with JSON, and here's how you would look up the address of a person with that same JSON document remotely using FalCore, which is just a proxy. Think of it as a proxy object with which you are working with the JSON. Now, as you can see here, the paths are precisely the same. We access the information using a series of key lookups. The only difference, as you can see here on the bottom, is that it's a push API. We're using, in this case, a synchronous API, but I want to be more specific and say that it's a push API. You give us a callback, and we invoke that callback. In this case, we're using JavaScript promises for those of you in the audience who aren't familiar. But long story short, it's an object that represents an eventually resolved asynchronous value. And so all this is really about letting the views actually dictate the data access strategy. Right now, in a lot of MVC frameworks, what you have is you have code that goes off and marshals data, either by calling web services or some other mechanism, and then hands it to view templates. And so these things are kind of decoupled. You can ask for more data in your view templates by changing them, but then you've got to go to this other place in code and change the code that marshals that data from the server. And we wanted to let the views actually control the data access. We would basically make the data access code go away and become transparent and allow you to bind to data that's in the cloud as if it was sitting right there in memory. And so here's an example of how we do this with React, which is the MVC framework that we use inside of Netflix. And so here, what we're doing is we are basically using the Falcor model as the model for this view, which is a person view. And in the render method, we are essentially requesting the name from the model dynamically and then converting it directly into JSX, which for those of you who aren't familiar, React actually pre-processes JavaScript and allows you to use HTML tags. It actually just turns it into plain old JavaScript objects. It's just to make it more readable. But that's essentially what's going on there. You're requesting the data on demand and getting it. And translating it directly into view objects. And so that's really all the data access code we have until we get into things like mutation. So we're really just pulling the data from the cloud. Now, there's really a concept that I think is incredibly important to understand as far as data transformation is concerned. And it's really the idea, the concept behind this framework, and actually some great different frameworks as well, which is this notion of three-dimensional data transformation. And really the idea that the what is the transformations or the data that we want to select. And the language or framework you use to describe those transformations should not constrain the other axes, specifically when that data must arrive or where that data actually lives. So let me elaborate on that just a little bit. So the what is quite simple. It's what data do you want? If I give you a JSON object, you pull that data out using a series of keys, and you do precisely the same thing here. I create a model, and in this case, I'm going to give it the URL of a remote JSON object. And then I can request, in this case, the name of the first genre list in Netflix. And I can also use this language, which is just a human-readable compression format for multiple paths. This is not a query language. I want to emphasize this is actually just a human-readable compression format for multiple paths to select, say, the box shot for the first, for the two titles in the first three genre lists. First two titles in the first three genre lists. Hopefully that's clear enough. It's not a query language, nothing complex. There's no where clauses or anything, just a shorthand for writing out all of those paths manually. So that's how you describe what you want in Falcor, by just looking up a series of paths. However, when the data can arrive, as I mentioned earlier, Falcor is reactive. And so whenever you make a request, it's essentially going to push the data to you rather than give you the data synchronously. Now, by being reactive, we buy ourselves the flexibility along the other axis, which is flexibility about where that data actually lives. By allowing us to push the data to you, we can pull that data out of an in-memory cache. We can go to the server, and we can pull it out of a database, or in memory, or from disk, or really anywhere. And so although these axes are orthogonal, in JavaScript, where it's a single-threaded language, you don't have the ability to spin up a thread, in practice, they're collapsed somewhat. If you have a synchronous API, you don't have any flexibility around the where axis. That data must be there in memory. And so by choosing a reactive API, it gives us flexibility about where that data lives. So what we know that in the JavaScript community, people love there's a huge proliferation of different async models, and for better or worse, and we are going to support them all, at least as many as we possibly can. And so promises, which are a part of the JavaScript 6 standard coming up, observable. I'm just curious, who's heard of observable? How many people in the room? Few folks. Okay, that's something we're actually proposing for JavaScript 7 as well. And think of an observable as like an iterator turned inside out. It calls you multiple times until it tells you that it's done. Who's familiar with Node streams? How many Node.js programs you got in the room? Okay. Few folks, very similar concept. And node-style callbacks, which is just pretty much a callback. We'll call you with the data or if an error occurred. Pretty bare-bones stuff. And so finally, where is the data, right? And this is really what Falcor is trying to get flexibility on. We're trying to present you with a common interface and allow that data to sort of live anywhere. And it can be local or remote. And so as I said earlier, you can start out working with an in-memory JSON object, and then you can sort of wrap that data in a proxy, which is the Falcor model, and then continue working with it with the exact same API. And that gives you the flexibility to later on move that data out to the server, say a node server, for example. And then we add a little data source, which is a communication mechanism. And so now we can, once again, notice the API hasn't changed. We're still using the same path, right? It's just become reactive. And when I make a request, it communicates with the server and makes the identical path request there locally on the server. marshaling the data, and then sending it back over the wire. Now, there's nothing particularly revolutionary about remoting a JSON request, right? This is relatively straightforward stuff, right? It could be a method call. It could be JSON. People do this all the time. They hide the network. But we're doing something a little more here. One thing that we are also allowing you to do, because most people don't store data in memory on a web server, right? On app servers, we like to be stateless, for example, is we want to allow you to be able to marshal that data lazily on demand. And so this precisely works exactly the same way actually a dynamic web server works. So if you go to Amazon.com, there's probably a good chance there's not an HTML file with your name in it when it says hi there, right? It's being generated dynamically based on some route matching in the URL and then going and grabbing something from the database. Now, we conceptualize our model as one big JSON object in the sky. And you can build a router that matches routes through that JSON object, and that's precisely what we do. So here we're actually matching two different routes through the JSON object, and as you request them, we will go and marshal that data, in this case, from two different data stores. Let's say the user information is stored in a SQL store because it's not changed very often, but maybe location is changed very often if you've got some sort of GPS tracking app, and that's stored in something with better scaling characteristics. So as you can see, though, not different than a dynamic web server where you match a route through an URL. Just as you can match a route through an URL, you can match a route through a path of keys. They're precisely the same thing. And so we're giving the appearance that this JSON object actually exists, but we're materializing it at runtime. So as I mentioned earlier, this stuff is done all the time, right? So what's different about this? Well, any framework that tries to hide the network from you, you should be deeply distrustful of. Deeply, deeply distrustful of. It is an extremely hard thing to do to hide a network from a developer and achieve good performance. In practice, hiding a network is a dangerous thing because network access is so expensive that it tends to be a leaky abstraction. If you attempt to hide the network from the developer and they don't know it's there, they might just start using it like it's in memory and end up with pathological request patterns, right? And so what we've taken we've taken a special care to try and avoid that. And so how Falcor manages to make this efficient, it's really three different things. Batching, caching, and path optimization. Batching is quite simple. If you make 16 different requests for paths, we wait until the next turn in JavaScript, which means we schedule the request, which allows you to make many, many different requests, and then we batch them up and then send them off. Now, batching APIs are everywhere, but that doesn't necessarily mean they're well done. In an RPC framework, people use batching APIs, but it's also very dangerous and difficult to do because you have no idea about what the side effects of a procedure are. And so order matters, right? It's very difficult to take an RPC framework and simply create a generic batch API where you can just take 15 procedures and call them in any particular order and send them off. And so it's very important that we are using idempotent operations. We talked earlier about REST. Well, the interesting thing about REST is it's got put and it's got get, right? Get is an idempotent operation, meaning you can repeat it as many times as you want and you're not going to have any additional side effects. Put, likewise, can be repeated as many times as you want. Put is where you replace an entire resource. It's a set operation, right? Well, it turns out a get and a set on a JSON object map pretty much one-to-one to those. If you repeat setting the same property in a JSON object 1,000 times, it will continue to have that specific property. And so we can rely on idempotence, if we're using the JSON API, to transparently batch certain operations, specifically gets and sets, because they map very nicely to gets and puts. And so batching is something that we can do because we provide these idempotent APIs. The second is caching. If you were to look under the hood inside of a Falcor model, what you would see was a partial copy of the JSON object out in the cloud. We don't have a complicated caching format. It's just a partial piece of the JSON format that's out there in the cloud, the pieces that you've asked for. That's all there is to caching in Falcor. Path optimization is much more interesting, and we will get to that. We can do certain things. We're trying to follow a RESTful model as closely as possible. We're trying to get the benefits of REST. But we can do certain things that are difficult to do with the traditional RESTful model World Wide Web today. So to demonstrate some of those benefits, let me talk about how you would build Netflix with Falcor. Let's actually go through a real scenario, somewhat constrained for the purpose of this talk. The first thing we need to do is define a model, right? And that's true regardless of whether you're using a network or not. When you sit down to build an application, you need to define a model. And Netflix's model, I assume, I hope, is relatively well understood. How many Netflix customers we have out of there? I'm just curious. I always love to see that sea of hands. So great. So I don't need to explain it to you. I think at least superficially, it's a pretty simple model, right? We have a lot of genre lists, which we recommend to you, personalized recommendations for each one of our members, right, based on your tastes. And then within those lists of genres, we have lists of titles. Right? So, that's from a simple high-level way to think about it, it's kind of like just a list of lists. It's a two-dimensional array even, maybe. And so if we were to try and come up with a JSON model for that, I mean, it'd be pretty straightforward. I think most of us could come up with a off-the-cuff JSON model that feels pretty good. So in this case, I've got what I can fit on a slide here. I'm essentially modeling the member, because at any given time, Netflix is being used by one particular member, right? And so each member has a list of genres, and within that, each genre has a name, and there'll be other properties that I've left off here, but it also has a list of titles. And so each of those titles in there is one of those titles we recommended, and that's sort of there along the x-axis. So as you can see, list of genres and list of titles. Each individual title there is in blue. So that's pretty much it. We're almost ready now to take this model and move it to the cloud. But there is one little hitch, and that is that the Netflix domain model is a graph, as most interesting domain models are, right? It's a graph. And just as an example here, we have two titles in two different lists, right? They're the same title in two different lists. And what I definitely don't want is I don't want to rate friends in suggestions for you and then scroll down only to find that my rating is not being reflected in the title when it's further on down the list. I don't want cache staleness, right? And so I want to make sure that that friends entity exists only once in cache or in memory or anywhere else for that matter. So as soon as I decided, it's nice in principle to have just JSON as your model out there in the cloud, but the reality is that it presents us with an engineering problem. Netflix's domain model is a graph, as I mentioned earlier, and JSON is hierarchical, right? It's designed for trees, as is XML for that matter. And so we really have two options, right? One is that we can explode it out into a tree by creating duplicates, but then that causes a problem for clients downstream because they have to sort of pull it apart and then turn it back into a graph again. And this is a problem presumably most web applications face, right? We've got application servers which presumably have graph data, but when they send it over the wire, they're using hierarchical formats like XML and JSON. Now, it's not rocket science to solve this problem. Most people come up with some sort of ID scheme, right, or some sort of linking scheme, Xlink, for example. And so what we've done is something quite similar here. Oops, little PowerPoint bug there. But the whole point is we want to avoid duplicates. There's Phil again, under his watchful eye. We want to avoid that cache staleness. And so what we've done at Netflix is we've introduced this concept called JSON Graph, which is a very, very simple graph modeling format in JSON. And the way to think about it is we just stole the Unix file system's great idea. The Unix file system is a tree. And if I say, for example, my operating system likes to have my pictures in my home folder. And I like to keep my pictures in Google Drive. So I'm sure there's some folks out there who, if you're good at Unix, you probably wouldn't think too much of it, and you would just set up what's called a symbolic link, right? So you could create a symbolic link, which is actually just a file that stores a path to some other location in the directory. And then, lo and behold, you've effectively created a graph inside of a tree, right? A Unix file system is a tree, but by creating this symbolic link that's nothing but a file with a path inside of it, you've effectively created a graph. And so that's a very, very nice way of modeling a graph in a tree format, and so we're going to do exactly that. One key thing, though, that I want to call out about a JSON graph is that every value, every simple primitive value in this JSON file is a resource. We want fine-grained resources. We want resources so fine-grained that they could be used by any Netflix team. If one particular Netflix team wants wants to grab 5 fields from a video, and another Netflix UI needs 2 fields from a video, we don't want to have to create custom endpoints. And so by creating extremely fine-grained resources, we're going to maximize our ability to sort of be loosely coupled across these different teams. So it's a very mechanical process. I don't know how clearly some of you guys can see that, but it's a very mechanical process to go from a JSON model to a JSON graph model. First you go through, you identify, first we'll just show path evaluation on a JSON model. I think you all know how it works. We just keep looking up keys until we find the value we're looking for, right? So I'm going to take this JSON model. In this case, we found friends, which is the name of the first title and the first genre list of your Netflix personalized titles. So let's take this model and let's convert it into a JSON graph. And it's very mechanical. First thing we do, we identify every entity with an ID. And then we create one location in the document, organized by the ID, a map effectively organized by the ID, where we put those. And so we take all the instances of those entities, and we just put them in that one location. And now we go back to all the other locations where we sort of had that entity before, and we insert a path. A path, the thing we've been using as the API for retrieving from the JSON model. And so it's basically just like Unix, where you would put a file path inside of a symbolic link. The only extra sauce we need here is that whenever we're evaluating a path, whatever kind of thing that we're using to evaluate path needs to understand the rules. But we do have another problem here, which is that now all of a sudden I'm using arrays to store paths, but presumably I could be using arrays to store data as well, right? I could be using arrays to store the list of subtitles for House of Cards, or just data, not actually a path to a location in the graph. And so we have a bit of a disambiguation problem. So here you can see I've highlighted the paths, right? They're in green, and they're basically just pointing to another location in the document. So I'll shrink this down just so we can get a clear look at it. Bear with me. Sorry, I was speeding through. So in order to disambiguate, what we do is we take every single list in the system, and we convert it, every single array, excuse me, in the system, and we convert it to a map. So we actually represent JSON arrays as maps. So if you can see what I've done there with the genre lists, previously it was an array, and now it's actually a map with ordinal keys. This is sometimes where I get a bit of a what moment? For those of you who are not familiar with JavaScript or JSON, arrays are maps. In fact, if you take JavaScript, for those of you who don't have much experience with JavaScript, and you dump a bunch of values in it, and then you reflect over the array and get out the keys, you will find it as a bunch of strings. 0, 1, 2, 3, 4, 5. Arrays are maps. And we can take advantage of that equivalent, not only to disambiguate. This is not just a trick to disambiguate between paths and lists, as I said before. There's actually a very good reason to store these as maps. And that's because what we want to do with the JSON graph is we want to allow you to grab just the data that you need for your particular use case. And arrays have certain guarantees. One of the guarantees about an array is that you should be able to for each over it in JavaScript. You should be able to synchronously blast through and grab all elements. I'm not sure what half of an array is. I suspect it's not an array. And if you were to ask me what half of an array is, that is the half that I've downloaded on the client from the server, I would be most likely to describe that it's a map, right? It's a series of keys that you've pulled out of that array. And so what we're doing here is not just a trick to disambiguate between paths and lists. I think we're actually being honest about this type system. Right? What we want you to do, certainly what I want to do with genre lists and what I want to do with these titles, is I want random access to them. I will be using them like maps, and that's what you do when you page a list. You use them effectively like maps. You grab ranges of keys, yes, but you're randomly accessing keys. And so this turns out to have a nice property as well, which is that on the cache, when I cache this list, for example, if you grab the last 10 items in a list, I don't create an array that is 5,000 items long and then only contains the last 10 items, right? This probably makes more sense for a format where you expect to be pulling down, sort of sipping data with a straw, and that's exactly what we expect. So by the time I'm all done, the JSON graph looks like this. And so every array can be disambiguated as a path, and we model lists as maps, which give us the ability to grab any section of them that we want. And the way to think about it is the JSON graph actually considers arrays to be values. They are atomic. You cannot ask for the third item in an array. You always grab the entire array. And so if you want to be able to page over an array, you model it in JSON graph as a map. So that's all there is to the JSON graph format. And if you model your data as JSON graph, you'll be able to remote it anywhere using Falcor. Now I want to show, though, that path evaluation has to work differently in JSON graph than JSON, right? In JSON, we just keep looking up keys until we find our data. Whereas in JSON graph, now we obviously have some sort of rule. And it's the same rule that the Unix file system applies when it comes across a symbolic link. Something has to be able to know how to evaluate that path. So now I'm going to take precisely the same path that you saw on the left-hand side, evaluate it against the JSON, and evaluate it against the right-hand side. So I'm going to wrap this in a Falcor model. I'm going to call get and pass in the path. It's a series of keys. And we are going to evaluate them. Now what happens is we run across as we run across the keys, as soon as we come across an array, because you're attempting to look up a key on an array, we know that it's not an array of data, but it's actually a path. So merely by the fact that you've asked for a key in it, you've effectively disambiguated it for us. And so now what we're going to do is we're going to take that path, and we are going to take all of the keys we've evaluated thus far, remove them, and insert that path at the front, jump back up to the root, and continue evaluating until we reach data. And so as you can see, the same path in both cases reaches the same piece of data. And that's all that the JSON Graph model does. It applies that path evaluation algorithm to get to your data. But you ensure you end up with no duplicates. This is actually useful regardless of whether you're remoting your data or not, because what you've got is a graph format that can be serialized at any time. This is something we very much take advantage of in Netflix. We will keep all of our application state in JSON Graph, regardless of whether we remote it or not, or whether it comes from the server, because of the flexibility of being able to serialize all of the state that you have at a moment. This is very useful for things like mobile applications. Interestingly enough, we've also optimized JSON Graph internally, where you can think of these paths as soft links. We actually make them hard links as we evaluate them. So we will actually stick pointers on those arrays that are hard pointers to the data. And so when you read it, it actually is much more comparable to reading from a tree structure, and you don't have to do all those extra hash lookups. And so we internally optimize it so that you can read very, very quickly. So now, here's the moment of truth here, which is the set operation, right? Part of the point of ensuring that we have no duplicates is that if we change one, we don't have to change it in multiple places, and we don't have to worry about stale cache. So on the left-hand side, if we set a series of keys, we manage to set rating, but unfortunately, there's a duplicate on the left-hand side, and so we end up with stale data. Notice on the left-hand side, because we have 2 copies of friends, we've set rating to 5 for one of them. But on the right-hand side, when we evaluate the path, so notice stale data. When we follow the path evaluation rules and call the set method, the idempotent set method in JSON Graph, we end up coming across the path, rewriting, and setting the one and only instance to the correct value. And so that's how we maintain cache consistency in Falcor. So JSON Graph is small resources. That's how we got fine-grained resources. We're doing very similar operations to what you would do in a traditional HTTP RESTful system, but because we're allowing you to access many, many resources in a single HTTP request, it now becomes cheap, in fact, to actually have a series of small resources. And now with one particular endpoint, we can serve many, many different devices that might select very different subsets of the overall graph. So once again, whereas HTTP REST will have these big resources like genre lists and titles, now you can get any one or any combination of these small resources. And as long as you batch them together in a single request, it'll be efficient. Now, of course, if we're doing this, we can't really rely on HTTP caching. We do not rely on HTTP caching, because what this looks like when we request these resources from the server is very much like RPC. We're passing a bunch of query string parameters, except in this case, the query string parameters are these paths that you see here. And so while we cannot rely on HTTP caching, we absolutely can build an in-memory coherent cache. We can do what I think most web applications do anyways, which is they build an ad hoc in-memory, this is single-page web applications, that is. They build an ad hoc in-memory cache. The difference is we're using RESTful principles to do that management for you. And so you effectively get the same no-touch, caching management that you would get if you had a traditional HTTP system, except we're doing it in memory. And another fringe benefit of caching in memory, even if you had HTTP caching, another fringe benefit of caching in memory is, of course, speed. If you're using a web application and you're scrolling through a list very, very quickly, you don't necessarily want to be parsing JSON from a string, right, that you've loaded off a disk cache. A disk cache is faster than the network, but it's not faster than memory. And so in a lot of cases, you want that memory cache, regardless of whether you have another cache layer or not. So as I mentioned earlier, we have the same idempotent operations, and we rely on those to keep a coherent cache. So now that we've got our model, it's just a JSON object, right? Just using the tools we have at hand, we're ready to build a virtual model. We put it in the cloud. So to build a virtual model, all you have to do is the same thing as building a dynamic web server. You define routes. And so I'm going to create a route for matching genre list, and then any particular index within the list, and then any particular index within the titles within that list. And then I'm also going to build a route for matching name or rating on any particular title. So this is very similar to using a regex for matching an URL. The difference is here we're more constrained because we're only matching paths, so we've got a slightly different, but it's the same idea. It's a regular grammar. We're matching it, and then we're taking that, whatever we match, and we're handing it off to a function that's responsible for realizing the results. And in practice, what that function is going to do, it's usually going to go off to some data store. Genre, in fact, in Netflix, all your personalized list information, because we have such a huge number of users in Netflix, is stored in a very scaled out Cassandra store. Right? Whereas videos, we have comparatively far fewer videos than we do users at Netflix, and so we put that in a different data store with different scaling characteristics. So when we assemble your list of personalized titles, it comes from actually many, many different data sources. But here, for the purpose of this example, we'll just show two. So here's an example of defining the title route, which is the simplest one in this particular case. And the goal is to just create that fragment of the JSON graph that you saw earlier. So I'm going to match any particular titles by ID, maps, path. So there we're asking for ID 2343 and 5123 and the name for them. And then that gets passed into this function path set. I should ask, actually, who is not familiar with this function notation here? Sorry, this is something I use rather liberally because it's from JavaScript 6, and I'm on the committee. But who has never seen this arrow function before? There's a couple people who have not seen the arrow function before. Who is familiar with arrow functions in general, like from other languages, maybe? So there's a lot of people. I'm hoping there's some overlap there. Long story short, JavaScript is growing up and getting an arrow function, which is a shorthand function. So functional programming, JavaScript's actually quite a capable functional programming language. It's just been painful because you have to type like 26 characters to create a function. Thankfully, that is going away in JavaScript 6, and you can now just write this little arrow. So what you're actually seeing up here is you're seeing a pattern that matches a path, and then you're seeing a function that gets the actual matched path. And what it's doing here is it's going to the database, retrieving it, and then building the fragment of the JSON graph that you would have returned had you been pulling it right out of memory. So virtual model path evaluation works like this. So let's start off with our simple model. This is on the client, right? All I'm doing here is thank you for the time alert there. All I'm doing here is I am creating that proxy model. I'm on the client. I've referenced my JSON graph out there in the sky. And I'm requesting a simple path, which is the name of the first title in the first genre list that we've recommended to you. So what happens when we get to the server is we hit this route. I'm going to redact the routes here, but long story short, we've got these two routes. We run the exact same query on the server. What happens is we match that pattern, because notice the path that I've requested matches this pattern. And code gets executed, or we go off to the database, and we realize dynamically a portion of this graph. Now what happens is that this requested portion of the graph is then inserted into the cache. And this is where things get interesting and different than the way a common dynamic web server works. The interesting thing about the World Wide Web is that it's flat. It's flat in the sense that we typically use URLs to describe structure, the structure of our hierarchy. The slashes mean something to us. But interestingly enough, to the average to all HTTP clients, they are utterly meaningless. HTTP clients do not know the structure of your URLs. They are nothing but a string to them. And that actually can be very inefficient for a variety of reasons. So in our particular case, what we can do is we can actually recursively consume portions of a path and then recursively match it, as you'll see. So, because of course there are many routes to the same information through a graph, right? And what HTTP will do is if you sort of hit a location that points to another location, it will redirect you, right? It's a 302 redirect. If I try and grab a resource here, well, a web server doesn't want to give me a copy of that resource because then I would be cache incoherent, right? If I can get the same resource at two different locations, then my HTTP cache would have that information twice and I'd have a stale cache. And so the right thing to do is for the web server to say, no, 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 the data's not over here, it's over there. But now we're back in the world of latency because it says, sends me a message all the way across the wire, and then I go all the way back to the server to pick it up. But wouldn't it be great if things were hierarchical, such that the server could actually evaluate that redirect on the server side? Now, there's such a thing as a server-side redirect, but that's not what I'm talking about. A server-side redirect does what I said earlier, which it basically creates the illusion that that thing is actually in two places. So it doesn't help us with our cache coherence problem. You'll see what I mean in just a moment here. So we've realized a portion of this path, but notice that this path only matched some portion of the path. We've asked for the name of that title, and this particular path matcher only matched genre lists 0, 0. And so we know there's still more to match. And so what we do is now that we've realized this portion of the path, we begin evaluating it. And we come across genre list 0, 0, we come across the array. And because we've come across an array, we know that it's a path, and it's time to rewrite that path and then attempt to match our optimized path. So we take this path, and then we optimize the path, and then we start from the root again. And so now we run it again through the router, and we match another path. And now we're going to go off to the video metadata service and realize another portion of the JSON Graph. We're going to stick that in the cache. And then after we evaluate it, we will finally end up with friends. Now, you might expect that what we're going to do now is return friends. That's what you asked for, right? You asked for the name of the first title in the first recommended genre list. But we don't. And this is where we differ from what HTTP does, because we're hierarchical, and HTTP is flat. We will return you all the pieces of the graph that we traversed in order to get to that value. What does that do for us? Well, notice here, I want you guys to think of these paths as little redirects. The difference here, however, is that in HTTP, you can only redirect from one specific resource to another specific resource. You can't redirect, to a prefix of a resource. If I ask you for lolamo/0/0/name, you can redirect me to videos1234 name, but you can't tell me that everything under lolamo00 can be found at videos1234. And that actually has a very serious implication for the web developer. It's because the web developer now needs to think about IDs. This is one of the hardest things to do if you're building a framework that abstracts away the network from the user. When you deal with remote data, you think about IDs. You have to think about IDs because there's tremendous consequences if you don't think about IDs. When you're dealing with in-memory JSON data, you don't think about IDs, right? There are IDs. They're the memory pointers. You don't think about them. You just walk across them because they're so cheap, right? But you can imagine now when you see the actual cost of going through all of the genre lists to get to one particular title, which is now 2 sequential database queries, you can imagine the cost of looking something up by relationship instead of identity. If I was to turn around and ask for the rating of this title, and once again pass in genre list 0, 0 rating, I'd be making 2 database calls that are sequential. Right? Wouldn't it be better if somehow the server could describe the hierarchical relationship to the client so the client could do the optimization on the client side before sending off to the server and then getting redirected? And that's what we're effectively doing here. Now, the client's gotten smarter. The client's learned something. The client has learned that the entity at genre list 00 has the ID 926. And it's totally transparent to the developer. Because if I turn around and I now ask for this exactly the way I would ask for it if it was in memory, which is genre list 00 rating, it will convert it into an ID for me because it will evaluate this path first against the cache. So let me show that in action. Not sure what happened there. Shouldn't be. Might have a bad connection here. I don't know if you can see that, but I'll go to the previous example. Long story short, that's what's actually happening here. Is that this path, if I was to change this to rating instead of name, instead of just blindly sending it off to the server to be evaluated again, we first evaluate it against the cache. We look up everything, we find out that genre list 00 is titles by ID 926. Then we look for titles by ID 926 rating right here, and we don't find it. And so we send off the optimized path to the server. And that's how we allow you to not think about IDs when you're working with data on the cloud. That's perhaps the most pronounced difference. When you work with network data, you all of a sudden have to think about IDs. You'll either look things up by identity or relationship, right? And in practice, it doesn't matter that much if you're working with in-memory data. But as soon as you're working with data that's out there on the cloud in a data store somewhere, IDs are like a shortcut through the graph. When you first request information about something, you almost always pull back the ID so that you can make following subsequent requests and use that ID and use it as a shortcut through the graph to improve speeds. With HTTP, you either don't get any smarter because you get transparently redirected to a location, right? I didn't learn that this whole prefix of path is all located over here. So the client didn't get any smarter because all it knows is that genre list 00 is actually videos123, genre list 00 name is videos123 name. It doesn't know that everything under genre list 00 is videos123. And so either the server has to go and get the entire list of links and then become smarter, but then, of course, the developer has to think about that, and we've got now multiple calls, because first I get the links, and then I follow up with further links, or I can have it recursively evaluate and walk down those links on the server. The only constraint, of course, is that you can access all of this metadata through one domain. That's how it works. That is the constraint that we apply. And if you have a web application that accesses most or all of its metadata through one domain, you can take advantage of that constraint to do all of this redirecting and recursive evaluation and basically the follow-up calls to retrieve more information on the server side using this technique. So I'll skip over this slide. I'm not sure why it's not working. And so as I mentioned earlier, type of the World Wide Web is flat. If you were to type at least the get and set operations, it looks like a big map from string to resource. And so if I request name, the server will tell me, okay, actually that's over here. It'll give me a 302 redirect. And then if I turn around and ask for the name again, at the actual correct URL, it'll tell me friends. Now that's a lot of back and forth, right? It's a lot of back and forth, and I haven't gotten any smarter. Because as soon as I turn around and ask for rating, well, it'll tell me, oh yeah, by the way, it's over here. Because we can't make any judgments whatsoever based on the structure of the URL. It's just a string. Anything that we might infer is purely by convention. So I eventually get the right answer. We can't do this in HTTP. And this is what we can do with Falcor, because Falcor is designed for structured data. And that makes sense when you're building an app server for a single-page web application, right? This is one of the things that doesn't map very well onto a system designed to disseminate research papers. But we think we can do better. So as I mentioned earlier, sets are idempotent, right? I can set, and what that means in practice is that when I set the rating on a title, I don't send it to the server, wait for a response, and then update my cache. I can set directly through my cache, update the cache immediately, and then send it off to the server. Now, I can wait for a reconciliation phase. If the server says something went wrong, that's OK. It'll come back and change. But when a member clicks the star bar on the Netflix title, they expect to see that reflected immediately. And this is one of these nice things where it just works, right? We can update it immediately without having to sort of hack it in. Because if we hack it in, what we're really doing is we're becoming tightly coupled. We're saying, well, we kind of know what this service is going to do, so we're just going to pack it in there anyways. That's one. Sets are very, very nice. They have this wonderful property of being idempotent. So what about non-idempotent operations? I said that we wanted the best of REST and RPC. But I haven't mentioned anything about remote procedure calls. Sets and gets are great, but you can't do everything with a set and a get. The most obvious thing comes to mind is just adding to a list. That's not a set operation, right? If I repeat adding to a list multiple times, I get a larger list. It's not side effect free. And so it's not that we're trying to design an entire system with only idempotent operations, but we're trying to take a system that's mostly about browsing static data and leverage as many idempotent operations as we can, right, and all the benefits we get from them. Now, every now and then, we are going to need to call a procedure, and we are going to need to potentially mutate a whole host of resources. So how do we avoid getting coupled? Because the problem is we've got this cache. We've got this big in-memory cache. And so as soon as I call one procedure on the server, I don't know anything that I think I know, because that procedure could have gone and changed 100 resources. And so my local cache may be completely out of date. So how do we reconcile these two things? Well, it's really straightforward, actually. We take functions and put them inside of the graph. So it's not just a function out there in the ether that returns transient data. Just like a JavaScript object contains functions, right? A JSON Graph object can contain functions. The difference is you can't download them. They're values. You can't look up keys on them, but you also can't download them. You need to use the call method to invoke them remotely. When you invoke a function remotely, it doesn't just return transient data, like you wouldn't have a 2 + 2 that returns 4. It mutates the graph and then sends you back one of two things. At the minimum, it sends you back the paths in the graph that have changed, that it has changed. And over and above that, it can also additionally, but it's somewhat discouraged, send you back the value post-mutation. And so it's as simple as that. When the function changes something, instead of the client having to be aware of what's being done, the function can send back the portions of the cache that have been invalidated, and that's how, transparently, we can keep the local cache up to date with what's happened on the server. Now, in practice, we actually recommend the server doesn't send back the post-mutation values. If I add to the front of a list that's 500 items long, I don't want to eagerly send back 501 items to the client. The whole idea behind Falcor is that it's designed for applications that show information to human beings in real time. And that means we want to be able to select the minimum possible subset to do something. And so if you happen to be looking at one page in a list with 5 items, go ahead and make that call. And call will also allow you to pass a series of paths that you want to retrieve post mutation. And so that's why call usually just sends back the parts of the graph that are invalidated, because you're going to follow up and ask for specifically the paths that you need to be up to date right now. So Falcors, we hope to gain all these things: cache consistency, loose coupling, low latency, and small message sizes. And thank you very much for listening.